We'll see the first problem in critical speed of shaft. So calculate the whirling speed. Whirling speed is nothing but critical speed. It can be said in two ways: whirling speed or critical speed. Calculate the whirling speed of a shaft 20 millimeter in diameter, 0.6 meter long, carrying a mass of 1 kg at its midpoint. Okay, let us have a look at this figure, right? The density of the shaft material is 40 megagram per meter cube, and Young's modulus is 200 giganewton per meter square. This should be in power meter square. Okay, assume the shaft to be freely supported. Okay, so it's a simply supported beam formula. That's what the meaning of freely supported, right? Let's list down the given data. D equal to 20 millimeter, 0.02 meter, 20 millimeters, 0.02. So length of the shaft is 0.6. Look at the diagram. You can see the entire length is 0.6. Mass is equal to 1 kilogram. So that you have to convert into weight and use it as a force. Okay. So density of the shaft 40 megagram, which is, so 1000 gram is 1 kilogram. Therefore 40 into 10 power 6 divided by 10 power 3 to convert it into kilogram. Therefore it becomes 40 into 10 power 3 kilogram per meter cube. Okay. So Young's modulus 200 giganewton per meter square, which is 200 into 10 power 9 newton per meter square. Have a good look at the diagram. So simply supported beam with UDL. The dead load is given here. Density of the shaft is given. With that we are going to use static deflection also in this formula. Okay. So first let us calculate the pre-required data. Moment of inertia first to find out. Pi by 64 d power 4. So d is 0.02. Therefore pi by 64 into 0.02 power 4. 7.855 into 10 power minus 9 meter power 4 is the moment of inertia. Since the density of the shaft material is 40 into 10 power 3, mass of the shaft per meter length. What is the L given in this problem? L is 0.6. But when you are doing the W, it should be done for 1 meter length. That I have already told you. Please keep this in mind. Per meter length is the actual formula. You have to, whatever may be the length, even if it is less than 1 meter, when you are calculating the weight of the shaft for substituting it in the formula, the 1 meter length is standard, that you should not change. Okay. So what is the weight of the shaft? How do you calculate? Area into length will give you volume, pi by 4 d square volume into L. So this is your volume. So volume into density is going to give you mass. Now mass into gravity will give you weight. Very simple. Okay. So these things you all know already. So calculate it. So length is 0.6 meter. D is 0.02 meter. Rho is 40. So here I am going to calculate per meter length. Pi by 4 d square L. Can one of you check this numbers? Is it correct? Pi by 4 into 0.02. I don't have a calculator right now because I am not sure whether this 0.6 is correct. See, as I told you, even I have committed the same mistake. Okay, it happens. When you are doing an exam, this naturally happens. Do not write this L here. Now this is the reason for all the mistake. This L is actually per meter length I am finding out, right? See, mass of the shaft per meter length, which means what? L should be 1 here, not 0.6. Okay, so this is not correct. This should not come. See, after telling you so many times, I have done the same mistake because I have listed down the L here. I have substituted it here straight away. Don't write the L here. So per meter length, I am calculating the weight mass. Okay, therefore pi by 4 d square. In place of L, you can put 1 or you don't put anything. The answer will not change. Okay, so if I write this, I am getting the same answer, 12.6. Okay, that is correct. So if I put 1, I am getting this answer. I've checked now. Okay, pi by 4 d square into 40,000 kilogram per meter cube. The mass is 12.6 kg per meter length. Okay, weight, you can, from this you can easily find out the weight, right? So into 9.81. So deflections I am going to calculate. The static deflection due to 1 kg of mass of the, there are two deflection calculations here. One is due to the point load, second is due to the uniformly distributed load. Okay, so first is WL cube by 48 EI. So W is 9.81, 1 kg. So convert it into Newton into 9.81, 1 into 9.81, 9.81 Newton. So it is the entire length of the shaft is 0.6 meter. The load is exactly acting at the center. For such a case, freely supported, simply supported beam, deflection exactly load at the center. The formula is, deflection formula is WL cube by 48 EI. Okay, this you have to by heart. Okay, so moment of inertia is 7.855 into 10 power minus 9. E is 200 into 10 power 9. So del is W is 1 kg into gravity. Okay, L cube, L is 0.6 meter cubit. So divided by 48, Young's modulus 200 into 10 power 9, moment of inertia 7.885 into this is 855. Okay, 7.855 into 10 power minus 9. Typing mistake. But the answers are correct since I have directly referred from the textbook. Okay, so when you are doing it, these mistakes will cost you the problem. 28 into 10 power minus 6 meter. So that's why I am telling you, keep practicing. Okay, since we are doing these things in a hurry, these mistakes occur. You can take some time, and if you can spot any mistake in the PPTs, you can tell me, right? So 28 into 10 power minus 6 meter is the deflection due to that 1 kg load. So that is 28 into 10 power 6 meter. So now due to the self weight of the shaft, the formula is 5 by 384 into W L power 4 by EI. Now what is this W? This W is what you have calculated. There was a mistake in the previous slide, right? I changed the number of the length 0.6 to 1 meter. Now that W is this. Okay. So W is 12.6 kg per meter length. That multiply 9.81, we get the weight due to weight per meter of the shaft. 123.606 is the weight per meter. This is per meter. Okay. That mistake should not happen again, all of you. So it's good that we have did that mistake. I myself have done the mistake, so that you understand it is very highly probable all of you will do the same mistake, because when you are writing down the given data L 1.6 meter above, and suddenly when you are substituting as L here, instead of putting 1, you will put that 0.6. Make sure it does not happen when you are calculating mass per meter length of the shaft. This is per meter length of the shaft. That mass I am multiplying with 9.81. 123.606. Okay, substitute it into the formula. So 5 by 384 into, this is weight per meter. So 12.6 kg per meter into 9.81. 123.606 into length power 4, 0.6 power 4 divided by 384 E I. E and I are same, no change. Okay. So now if I calculate it, static deflection due to the self weight of the beam is 0.133 millimeter. 0.133 into 10 power minus 3 meter. Okay. So now I can go for static deflection due to 1 kg is 28 into 10 power minus 6. Due to self weight is 0.133 into 10 power minus 3. Right. So now I can calculate critical speed of the shaft. First find the natural frequency using Dunkerley's formula. 0.4985 divided by square root of individual deflections plus self weight deflection divided by 1.27. Don't forget that. So this divided by 1.27 is only for the self weight component. Other deflections it will not come. Divided by 1.27 will not come. Okay. So static deflection due to 1 kg point load is 28 into 10 power minus 6. So static deflection due to self weight is 0.133 into 10 power minus 3. Substitute the numbers. So 0.4985. So this is your 1 kg load deflection. This is your self weight deflection divided by 1.27. Solve all the numbers. Use proper parentheses in your doing it in a calculator. You have to put a bracket like this. Otherwise, all the answer will go wrong in a calculator. Okay. So it comes around 43.4 hertz. Natural frequency, linear natural frequency for the given configuration of the beam is 43.4 hertz. Now this is numerically equal to my revolution per second critical speed. Okay, 43.4 revolutions per second. Okay, so we know that whirling speed of the shaft in revolution per second is equal to frequency of the transverse vibration in hertz. Natural frequency actually. This is not frequency. This is natural frequency. Any frequency is frequency. Natural frequency means what? You just disturb it and leave it. It vibrates in its own frequency, particular frequency. It happens every time you do it. You take a spring, elongate it, and leave it without disturbing. It happens. It vibrates and for some period of time in its own frequency. Now that is natural. Without getting disturbed, you leave it as it is. It vibrates in its own frequency. That is 43.4. Okay. Now this natural frequency NC, critical speed of the shaft. The shaft will break if you rotate it 43.4 revolution per second. Okay, 43.4 hour. It is written as 3 here. 43.4 revolution per second into 60 will give 2598 RPM. So revolution per second I am converting to revolution per minute by multiplying it with 60. So that is your critical speed of the shaft. If you rotate the shaft at exactly at 2598, your frequency will match the natural frequency of the shaft. Resonance will occur. Your denominator of that fraction of y equal to plus or minus e divided by omega n square minus omega square divided by omega square minus 1. When your frequency of rotation, angular velocity matches the natural frequency 43.4, this will become 1 and 1 and 1 get subtracted, the denominator will become 0, therefore your dynamic deflection due to centrifugal force will become infinity. Now this condition is called resonance condition. Okay, I have to, one thing I want to make it clear, what will happen if I go above 2598? Will the shaft break? It will not break. It will start deflecting in the negative condition. Okay, so you have to make sure that the resonance does not occur. Even if you go above resonance speed, nothing will occur. It will not break. Deflection will be in the negative direction. Below the resonance, it will be in the positive direction. If you match the resonance, exactly the speed matches the natural frequency speed, your shaft will break. Now that is called as critical speed. Not below, not above. Nothing will happen. If you go above that speed, nothing will happen. Below the speed also, nothing will happen. If you match the resonance, natural frequency condition, your shaft will violently vibrate and the deflection, dynamic deflection y will become infinity and your shaft will eventually break. Okay, so whirling speed of the shaft is 2598 RPM, right? So that completes the problem taken from your Kurmi textbook, problem 20.